देखिए बच्चों, फर्स्ट क्वेश्चन अगर हम डिस्कस करें, द अमाउंट ऑफ वर्क डन बाय द एक्सटर्नल एजेंट टू टर्न एन इलेक्ट्रिक डाइपोल ऑफ डाइपोल मोमेंट फ्रॉम दिस पोजीशन 45 डिग्री टू दिस। तो कंसेप्ट इस क्वेश्चन के पीछे ये है कि जब आप डाइपोल को टर्न करते हो, मतलब बेसिकली क्या होता है कि जब हम किसी इलेक्ट्रिक फील्ड के इनसाइड एक डाइपोल को प्लेस करते हैं, सपोज ई इज द इलेक्ट्रिक फील्ड एंड देयर इज सम डाइपोल एट सम थीटा एंगल, तो हमें पता है कि डाइपोल को जब आप इलेक्ट्रिक फील्ड में किसी थीटा एंगल पर विद रिस्पेक्ट टू द इलेक्ट्रिक फील्ड प्लेस करते हो, तो उसकी एक पोटेंशियल एनर्जी का फॉर्मूला बनता है विच इज माइनस टाइम्स पीई इनटू कॉस ऑफ थीटा। अब इस क्वेश्चन में इनिशियली वो 45 डिग्री एंगल पर है, देन इट इज एट 270 डिग्री एंगल, सो यू कैन फाइंड आउट इट्स इनिशियल पोटेंशियल एनर्जी बाय minus of PE into cos of 45 degree, which is 1 by root 2, and then you can check the final potential energy by putting theta as 270 degree, and when you put theta equals to 270 degree, which is a zero value, cos of 270 degree comes to be 0, and therefore the final potential energy will be zero value, and therefore the change in potential energy, which is the amount of work to be done, this is the external work which is asked, which has been asked in this question, that external work is change of potential energy, so the answer should be W external equals to final potential energy minus the initial potential energy. The rest you just put the values, numerical values, and solve the question, you will get the answer. Coming to the second question, a small test dipole of moment is mounted at a distance from the center of a smooth metallic sphere. Notice that it is smooth metallic sphere. The sphere has this radius and certain charge. The test dipole is at right angle to the line joining with the center of the sphere, and so on, which means there is some spherical charge, a spherical metallic charge, and from the center of that sphere a line, a radial line is coming, and a dipole is placed perpendicular to this line. Okay, so this is the orientation of dipole, which is perpendicular to the radial line. Now we have to calculate the force on this dipole. Sorry, we have to calculate the torque necessary to hold the dipole in this position. Okay, so the first question is why there is some requirement of torque to hold this dipole, because this sphere which has some charge, this is sphere which has some charge of say capital Q, this sphere will create electric field around it, and when this sphere will create electric field around it, this dipole is perpendicular to that electric field. Notice that dipole is a very small dipole. Since the dipole size is very small, very small dipole, we can think of a dipole in some kind of a uniform electric field, where the electric field value will depend upon the position of dipole from that sphere. So if the dipole is at r distance from the center of our sphere, then this electric field will have magnitude of K into charge capital Q by r square. And perpendicular to this electric field, there is some dipole. We all know that this external electric field will always try, this external electric field given by the sphere will try that dipole is aligned with this electric field. So this will be torqued by this our electric field of sphere. Electric field by this sphere will generate a torque on the dipole to make the dipole get aligned with electric field of sphere. And therefore we need some external torque opposite to the torque by this electric field to hold it. So our external torque which is required to hold the dipole in this position should be equal to the torque which is given by the electric field, and the torque on a dipole in uniform electric field, especially when the dipole and electric fields are perpendicular, that torque is given by dipole moment multiplied by electric field. Though the actual formula for that torque, actual formula for the torque is Pe sine theta, but since the dipole and electric field they are making 90 degree angle, the sine of theta will become 1, and therefore torque is simply P into E. And again, just calculate the values. Your answer is ready. Third question. A charge Q is distributed over two concentric hollow spheres of radii small r and capital R. Okay. So there are two concentric spherical cells One has a radius of small r, inner one, and outer one has a radius of capital R. And some charge is given. So this is small r is the radius of inner one, capital R is the radius of outer one. Some charge is given in such a way that the surface densities are equal, which means if sigma is the density on the inner sphere, the sigma is also the density of outer sphere. So sigma, which is the density of charge, multiplied by the total area on which we are distributing the charge. Total area of distribution of charge is 4 pi r square for the inner sphere and plus 4 pi capital R square for the outer sphere. So surface charge density into total area on which the charge will be distributed. This gives the value of charge capital Q. So we get sigma from here, and the value of sigma will be now Q by 4 pi and then a small r square plus capital R square. And it gives me the charge on individual spheres now. If Q1 is charged on the inner one and Q2 is charged on the outer one. So now we can find out the charge on inner one Q1 as surface density into the area of inner sphere. And also we can find the charge on outer sphere as sigma into 4 pi R2 square. Sorry, it should be capital R, not R2. It should be capital R square. So if we substitute the values of sigma, just put the value of sigma, you get the values of Q1 and Q2. This sigma which we have calculated, if we put this value of sigma here and also here, then you get the values of Q1 and Q2, which comes out to be like Q1 equals to Q times small r square by capital R square plus small r square. And then Q2 comes as capital Q times capital R square divided by capital R square plus small r square. So now you get the charge on both spheres. Now we have to find the potential at the common center. So the potential at this common center will be the potential by inner sphere, which is KQ1 over small r, and also the potential at this common center will be because of the charge of outer sphere. So now it is K times Q2 divided by capital R. Both the spheres will create some potential at the center point. And just put the values of Q1 and Q2, you will get your answer. Then coming to the fourth question. A spherical droplet having a potential of this much is obtained as a result of combining 125 identical droplets. Okay. So let these identical droplets have radii of smaller, and that big drop, that is spherical droplet, let the radius of that is capital R. So first we will find relation between these two radius by just equating their volumes. So 125 small droplets have volume of 125 multiplied by 4 by 3 pi small r cube, and it should be the volume of that single drop, which is obtained by merging these 125 droplets. So it is 4 by 3 pi capital R cube. Okay. So you get capital R and small r a relation, which is like capital R equals to 5 times of small r. Also assume that Q is the charge on these individual droplets. And since we are combining 125 such droplets, and if a small q is charge on each single one, then the total charge on bigger sphere will be 125 q, conservation of charge. And therefore, the potential of that single small droplet, potential for the single small droplet can be written as K, charge on that single small droplet is small q divided by capital R. Whereas the potential of that big drop, which is obtained after combining these 125 droplets, will be K. Total charge on that single drop will be 125 times Q over the radius of that single drop, which is capital R, 5 times of small r. And this value is given as 2.5. 2.5 is the value for this expression. So you substitute here, and then your answer will be 25 into 2.5. This is the final answer. So now that answer will be like 5 125 upon 5 will be 25, and then it is 2.5. So that is the answer, potential of the constituent droplet. I'm sorry. This 2.5 is not the potential of that single drop. Actually, the 2.5 value is given as the potential of this value. This term is given as 2.5. And we have to find the potential of single constituent droplets, which means this is unknown portion. So this will be 2.5 divided by 25. That is 0.1. Fifth one, question number 5, which is straightforward formula based question. Question number 5 is a straightforward formula based question. It is talking about dielectric sphere, which is basically non-conducting insulating sphere. And for any uniformly charged non-conducting insulating sphere, the expression of electric field at a point which is inside that sphere is K capital Q, which is the total charge of that sphere, into small r, which is the distance from center, by capital R cube. And also the electric field formula for outside points. At any point which is outside that sphere, the electric field is given by K times capital Q over small r square. Again, small r is the distance from center. So in this question, this E1 is the electric field at inside point, for which this small r has to be r by 2. And in this question, this outside electric field is given as E2, for which this small r value is 2 times of capital R, and then you can find out what is the ratio E1 by E2, and also what is the relation between E1 and E2. Now, next question is sixth question, in which we have a thin conducting spherical shell. Again, notice that it is a conducting shell of inner radius capital R, carries some charge density sigma. Which of the following is true? Not true. Okay. Which of the following is not true for this system? Electric field inside the shell is 0. This is perfectly true statement. Is a true statement because we are talking about a conducting shell, and for any uniformly charged conducting shell, the electric field inside that shell will be 0. Electric potential at the center of that shell will be sigma r by epsilon 0. Let me check this expression. The potential inside any uniformly charged conducting shell will be 1 over 4 pi epsilon charge of that sphere upon capital R. So just multiply it with R and divide with R, and recall that this 4 pi R square becomes the surface area, and Q upon this surface area can be called as sigma. So it is sigma R over epsilon 0, and that means this P statement is a true statement. Electric potential difference between the center of shell and surface is 0. This is again a true statement because uniformly charged conducting shell, inside uniformly charged conducting shell, the potential remains constant everywhere. For any uniformly charged conducting shell, if it is a conducting shell, it is uniformly charged, so potential at center is same as the potential at surface, and also it is the same potential anywhere inside that shell. So there is no potential difference. Again, a true statement. Electric potential at distance r by 2 from the center, obviously it is the wrong statement. So this is our option, because we have to choose the statement which is incorrect. For the seventh question, there are 3 identical springs holding 3 charges. 3 charges, and the 3 springs are holding them. Force constants are given. If the spheres are given some charges, then the extension, assuming to be very small as compared to the natural length. What does it mean? Assuming it to be very small as compared to natural length of a spring. Why this statement is given in this question? Suppose the original length of a spring is L, and if the extension is very small, so you can think as the you can imagine, you can approximate the separation between the 2 charges as a constant separation of a small L. So if extension is, if I assume that the extension in the spring, they are extended, let's say by small x, then according to the Hooke's law, these extended springs at any moment, suppose I draw the free body diagram of this charge, and if I draw free body diagram for this particular charge or any other charge, then this particular charge will be repelled by remaining two charges along the sides of triangle, and those repelling forces will be the Coulombic forces kq square divided by L square, and another repelling force on this charge will be kq square by L square. These two repelling forces are coming from the remaining two charges. Like if you are drawing the free body diagram for this particular charge, then these two remaining charges will exert repelling forces. Also, the two springs which are extended by small x, there's a horizontal spring will pull back, will apply a force according to the Hooke's law, kx, and also this second spring will apply a force kx just to restore the length of spring, and therefore these forces will balance each other for the equilibrium, and so you can say that kx is simply kq square divided by L square. Remember that this k is spring constant, and the another k which I have used for Coulombic force is basically the Coulombic constant, which is 1 over 4 pi epsilon 0 times, sorry, nothing. This is just a constant, so it is 1 upon 4 pi epsilon 0. So this is the spring constant and this is our Coulombic constant. Take care of these two constants. So I think B is the correct option for this question. Just balance these two forces, you will get the answer, and B should be the correct option for this question. Right. For question number 8, there is some electric field and potential at point 1, 1 is given, and there is another point of 2, 2, and we have to find the potential difference between these 2 points. But the concept for this is the potential difference between the 2 points in any electric field. The potential difference between the 2 points in any electric field is given as the integral of electric field with respect to some position vector between the point 1 and point 2, and it can be done along any path. So if I apply this equation, the E vector is minus AX I cap minus AX I cap, and then it is minus BY J cap dot, and this dr vector which can be written as dx I cap in a two-dimensional differential form. The displacement can be dx I cap plus a dy j cap, and if I take this dot product, if I take the dot product, I get first integral as a minus ax dx, and then second integral I get as minus by dy. So the limits for the variables dx and dy are 1 to 2, and also here 1 to 2, and then just solve this integration, get the answer. Question number 9 is the force on a charged particle is given by. So a force is given in this question, and remember that this for electric field, the line of electric field is same as the line of force. This is for the line of only for electric field, because F equals to QE, the relation is F equals to QE. So the line of E and line of F, they are always the same lines. And this force is given in some XY form, and we have to draw in YZ plane. So remember, there is that we have to draw the force lines. We have to draw the line of force, or you can say we have to draw the line of electric field, but we have to draw these lines in YZ plane, and the force does not depend upon Z. And in YZ plane, remember that in YZ plane, the coordinate X will be 0. And therefore, the force can be written as this given force can be written as constant into y square times k cap. So this k cap is basically the direction of the force, and this constant into y square is the magnitude of the force, which means the magnitude of a force is a function of a y coordinate. So higher the value of a y, higher will be force, lesser the value of a y, lesser will be the force. But because it is y square factor, so even if y is positive or y is negative, the direction of force will remain same. So the force will always be along k cap, positive z axis, no matter y is positive or y is negative, because there is y square in the sum. So y square will always be a positive value, and then as the value of y increases in magnitude, the force also increases. So it should be a graph of like a parabolic type curve, and the only correct option here is, and also if we look at the graph, a graph is plotted on zy plane. So even for y positive and y negative, you will get, and depending upon the constant, if it is positive constant or negative constant, because the sign of constant is unknown. So it may be a positive constant, it may be a negative constant. So the graph can be either plus y square or minus y square. So if I plot plus y square graph, it will be something like this. According to mathematics, plus y square is like this, and minus y square will be something like this graph. So the C option is the correct option. Okay, right. 10th. Here the line charge is along infinite line charge is along y-axis, and the dipole which is placed is also along this y-axis. Both are parallel, and the maximum potential energy of this dipole will be, the maximum potential energy of this dipole will be, remember dipole and line charge both are parallel to each other. Okay, so what will happen here? Sorry, mouse is not working. Okay, so in this 10th question, this is not working, I'm sorry. So there is infinite line charge. According to this question, this infinite line charge is along y-axis. Suppose lambda is the linear charge density, and the dipole is placed parallel to it. So what will happen? This infinite line charge which will create some electric field, and this infinite line charge will create electric field perpendicular to this line, and this electric field which is created by this wire or a line charge, this electric field is perpendicular to the dipole, and so the dipole, so this dipole will experience some kind of torque by this electric field, and very soon it will be aligned with the electric field. Now we have to solve this maximum potential energy of the system. What can be the maximum potential energy for the system? Remember, this orientation is not the orientation of maximum potential energy, because a dipole experiences a potential energy in external electric field by this relation minus of P E cos of theta. And we all know that cos theta has a range in between -1 to +1. So the maximum potential energy of the dipole can be obtained by simply dipole moment into the electric field. And this electric field which is created by this infinitely long wire will be lambda over 2 pi epsilon 0 into r. Let's calculate the values for 11th question. For this 11th question, okay, just remember, there is something very critical in this question, a conducting loop. This is a loop, but it is a conducting loop. And according to the property of a conductor in electrostatic, any conductor in the electrostatic is always equipotential. We all know that electric field inside this conductor will be zero, and in absence of electric field, there cannot be potential difference of this across this conductor, whatsoever the reason is. As long as you are dealing with a conductor in electrostatic, remember that electric field inside a conductor has to be zero, and therefore the potential difference across any length of the conductor will be zero. So it should be C option. 12th, there is electric field, the dielectric constant is given, epsilon is given, and this is simply energy density. Okay. So the electric field energy density has a formula of half epsilon E square, but this is only when you are calculating energy density in some free space. And if we are calculating energy density in dielectrics, then it will be multiplied by that dielectric constant also. So this is in some medium. And here we have here the electric field is uniform, 4 I cap minus 3 j cap, and a medium is present which are with a given dielectric constant, and the rest we have to put the values. And this electric field will be the magnitude of this vector, which can be obtained by the very basic concept of the vector, how to find the magnitude of a vector. For 13th number question, frequency of oscillation of electric dipole of this and rotational inertia this in a small electrical. This is a very standard result of time period of oscillation of dipole in the electric field. And we know that the time period of oscillation of dipole in the electric field is 2 pi root of I over QE. The basic formula of oscillation time period, and then frequency will be simply 1 upon time period. You have to just put the values in the formula to get your answer. 14th number question, there is electric field in this region between this point, and electron having this much charge projected with velocity itna, and when the electron leaves the region of electric field, its velocity is okay. Okay, so okay, very good. There is electric field along y-axis. If you read this question, the electric field is given is along the y direction. The electric field given along this y-axis, and electron having negative charge, which means a negative charge enters in this electric field with some x component of the velocity vx, and also with some y component of the velocity vy. Okay, there is some x component of velocity, there is some y component of the velocity. Remember, this is the initial velocity of electron in which x component is present and y component is also present. Both the components of velocities are there. Now this electron having negative charge will experience a force of this electric field in this downward direction. The force by electric field on a negative charge is against the electric field direction. So there will be a force on the electron in the downward direction, which will change this y component of the velocity during the motion of particle. So as this electron will travel through the region of electric field, the y component of the velocity will be reduced because of opposite force. And you can compare this motion as projectile motion of a particle in gravity. So this electron will move something like parabolic. It will move something on a parabolic path. And when it will leave this space of electric field, the horizontal component of the velocity, this velocity Vx will remain unaffected, because there is no acceleration in that direction. There is no force in that direction. So therefore, this x component of the velocity will be same as it was at the time t equal to 0. But in y-axis, along this y direction, which is parallel to the electric field, along this y direction, which is parallel to the electric field, the velocity component in the final stage will be something different than the initial velocity due to the force F equals to QE. And this velocity can be obtained by the third equation of a motion, which can be written as Vy square. And this force when divided by mass will give you some acceleration in y-axis. So this minus 2 times acceleration on a y-axis, and then the displacement. Should know the displacement along y direction. Or you can say that Vy, by the first equation of motion, you can write it a Vy minus Ay times of t. And if it travels L length in this electric field, if it travels L length in the horizontal direction, because this x equal to 0 and x equals to 9, this is basically the horizontal displacement information for this L. So this L is given as 9 centimeter. And since the horizontal motion is without any acceleration, this L should be the horizontal velocity Vx multiplied by time. From here you can get the value of time, which is L upon Vx. And and after you get this value of time, you substitute this value of time at this point, you will get the value of a Vy dash. And remember, this Vx remains unaffected. So the final velocity in a vectorial form can be written as Vx I cap and plus that Vy dash j cap. Rest is the calculation. Now 15th question. A small sphere of this much mass carrying a charge is connected with a light, flexible and inextensible string of length this much and the vertical circle if in the vertically upward field of electric field this exists. Okay, very good. So there is a vertical electric field known, and it has certain value, and we have a sphere with some charge, and that sphere is having a charge of say q. And then calculate the minimum velocity of a sphere required at the highest point so that it may wait to complete the circle. Okay, we want this sphere to complete a circle. For that, what should be the velocity at the highest point? Okay. Now, if I calculate the forces on that charge particle, it has a mass of 0.5 kilogram. It has certain charge also. There is electric field present. So if you plot the free body diagram, it will have a force of gravity in the downward direction, which is mass into g. And the gravity force, which is mass into g, will be 0.5. If I take g as 10, then it will be 5 Newton in the downward direction. And also a force by the electric field, which is QE. That force, if I calculate, Q is 1100 microcoulombs and the electric field is 10 to the power 4. So if you take the values of Q and E from the problem and then solve it, Q into E comes as 11. So 11 Newton force is upward and 5 Newton force is downward, which means the overall there is a 6 Newton net force in this question. And the 6 Newton net force in this question is in the upward direction. And when this net force 6 Newton in the upward direction divided by the mass, so this 6 Newton force and divided by mass gives me acceleration of 12 meter per second square. And this 12 meter per second square is which is the net acceleration in upward direction. It can be compared as effective gravity, which means in this question the effective gravity is not in the downward direction, effective gravity coming in the upward direction. So imagine a situation in which gravity is upward. And remember the chapter vertical circular motion of class 11th, work energy power. In the chapter work energy power, when a pendulum was given velocity of root 5 GL at the bottom point, it was able to complete the circle. In that case, that velocity at topmost point was coming as root of GL. But for this question, the direction of gravity was considered to be in the downward direction. Now we are dealing with a situation in which there is some effective gravity in upward direction. So we will change the two results. What used to be what used to be at the bottom point of this well-known case? What used to be at the bottom point of this well-known case should be now at the topmost point. And take G effective. And what used to be at the topmost point of the well-known case, which is root GL, should be now at the bottom of this vertically upward G effective case. Since the direction of gravity is flipped, so bottom and topmost points are also flipped. Root 5 GL, which was the velocity at the bottom point of that case where gravity was downward, should be now the velocity at topmost point where the gravity is upward. So our answer will be now, for our question, the answer is root 5 G effective into L, and G effective is 12. So this value should be root of 5, G effective is 12, and the length is given as, some length must be given in this question, 60 centimeter, 0.6. So it is 6 meter per second. Now 16th question. A positively charged sphere of this much mass is attached by the spring of force constant, and the sphere is tied with a thread so that the spring is natural length. Very good. Another negatively charged sphere is fixed with the floor vertically below the first sphere. The initial separation between these two is 50 or the centimeter. A charge on each sphere this much. Calculate the maximum elongation in the spring. Okay. So this is something like you have a vertical spring and a charge is at the bottom of that spring, which is positively charged sphere. There is a plus Q charge. Another minus Q charge is also there, but that minus Q charge is fixed. Negatively charged sphere is fixed with the floor, right? And these two are separated. These two are separated by initial distance of 50 centimeter. Let it be D naught. This D naught is given as 50 centimeter. Okay, this initial separation of 50 centimeter. And spring is in the natural length. So this L naught is the natural length. It has no elongation. And there was some thread holding this charge from falling down. So when you burn the thread, when somebody burn that thread, this positive charge will start moving downward, and it will move up to a place where the elongation is maximum. And let this maximum elongation is x. At that maximum elongation, the separation between our two charges will be D naught minus x. And now if I use conservation of mechanical energy for this system, then at the initial moment, if I take spring, the two charges, earth, everything as a part of our system. So if I take spring, earth, the charges as a part of system, so the mechanical energy of system should be conserved because there is no external work is there, and therefore initial energy of spring plus initial electrostatic energy, ES, which stands for electrostatic energy, and plus initial kinetic energy, should be the final spring energy plus final electrostatic energy and the final kinetic energy. Plus K final. Now the initial spring energy is 0 because the spring was normal. Initial electrostatic energy was K Q1 Q2. over d naught with a negative sign. And the initial kinetic energy was also zero because the system started with rest. Final spring energy can be written as half kx square in terms of final electrostatic energy between the two charges will be k q1 q2 with a negative sign upon the separation in the final stage is d naught minus x. And the final kinetic energy is also zero because the system comes to the rest. If I start from rest, then finally it comes to the rest and just put the values, you will get your answer. 17th. This particular question in which there are two spheres of radii 5 and 10 centimeters and they are very far away. The distance between them is far and they are connected by a conducting wire. This is a very well-known question. We have already done in this class, in our class, that when two spheres, whenever two spheres of different radii R1 and R2 at large distance, the two spheres of radii R1 R2 at large distance, if they are connected by some wire, then the potential is simply the total charge upon 4 pi epsilon 0 R1 plus R2. This is classroom illustration and you can follow your notes. Joining of two spheres at a large distance. For 18th question. A solid conducting sphere has a charge q surrounded by uncharged concentric conducting hollow spherical shell. Let the potential difference between the surface and that is this. Okay, very good. So there is a solid conducting sphere. A solid conducting sphere, it has some charge and it is surrounded by some metallic shell also with some another charge. And in this case, the potential difference is 12 volt. Very good. 12 volt is the potential difference between these two, which is inside we have a solid metal and outside we have a hollow metallic shell, and the potential difference between these two is 12. Now, some charge is given to the outer shell. Shell is now given, that outer shell is now given a charge minus 2q, the new potential difference between the same two surfaces. Remember, the potential difference between these two, between this solid surface 1 and the metallic surface 2, the potential difference between these two, v1 minus v2, is the integral of electric field dot dr from point 1 to point 2. And this electric field will be obtained by this Gauss law. So if I try to find the electric field at a point in between these two surfaces, if I take a point between the two surfaces, to get the electric field at this point, what we will do, to get the electric field at this point, what we will do is to draw a Gaussian surface. And if you draw the Gaussian surface present between solid metal and that metallic shell, this Gaussian surface between the two metallic surfaces will include the charge of inner solid shell. No matter what is the charge on this outer shell, let the outer shell has a charge of q1. But when you will calculate the electric field between the solid surface and this metallic shell by the Gauss law, and Gauss law says that the electric field and the area of Gaussian surface should be the charge which is inside that Gaussian surface divided by epsilon 0. This by epsilon 0. So the charge which is present on the outer shell will not be used in calculation of the electric field by Gauss law. And when that electric field, that the charge on the shell is not used for the calculation of the electric field, which means this electric field will be independent of that charge. Q1 will not appear in calculation of electric field. So if you change Q1, nothing will happen. Electric field will not change. And when the electric field will not change, the required potential difference will also not change, and the potential difference will remain 12. 19th, a small metal sphere having this much charge is held stationary by insulating supports. A second metal sphere of this much charge and mass is projected towards Q1 when the two are 1 meter apart. Q2 is moving with Q1 at the two spheres can be treated as a point charge, and the effect of gravitation elected. Find the distance between the two spheres. What is the speed? So at a distance of 1 meter, at a distance of 1 meter, speed is given, and at another distance of 0.5 meter, the speed is required. It is simply a problem based on conservation of energy, and the two spheres are like point charges as stated in the problem. It is simply the initial electrostatic energy, which can be K Q1 Q2 upon R initial R1 plus initial kinetic energy of that moving charge half m V1 square. And then in the final stage, when the separation becomes 0.5 meter, it is K Q1 Q2 upon the new distance R2. R2 is 0.5 and R1 is the initial distance 1. V1 is this 20 meter per second. This is a V1. And then the second is speed of V2, which is at a distance of 0.5 meter, is required in this question. Just solve the problem, put the numerical value, you will get your answer. 20th. This 20th question. So for this 20th question, two identical balls having like charges are placed on a certain distance apart, repel each other with a certain force. Two identical balls having like charges. Okay, identical means geometrically. Geometrically, they are identical. Identical does not mean they have same charges. Identical means geometrically their shape and size are equal. So if one sphere has a radius of r, another one is also of the same radius, and suppose their charges are q1, q2. So the repulsive force between these two spheres will be according to this Coulomb's law, and k q1, q2 upon r square, small r square, where small r is the distance between center to center, center to center distance. And now they are brought in contact. So the two spheres are brought in contact and separated to half their initial value. So what will happen when you brought them in contact? Brought in contact will redistribute the charge. When the two spheres are brought in contact, the charge redistribution will take place, and because the two spheres are identical, now they will redistribute the charge by same amount. So after they are brought in contact and then separated to half distance, which is small r by 2, the charge on each one will be now total charge q1 plus q2 divided by 2. Bringing in contact will redistribute the charge. Since the spheres are identical, the charge distribution will also be identical. And now the force between these two. Now the force between these two is given as 4.5 times of previous value. So previous value was F, which means now the force is 4.5 F. And this 4.5 F should be K times Q1 plus Q2 by 2 is the charge on one sphere. Also the charge on second sphere. So square and divided by the new separation is R by 2 square. Just calculate this, you will get your answer. For 21st question. For 21st question, we all know that there is a standard result in which if there is circular area and a point charge Q is on its axis at some z distance, and this circular area has a radius of r, then we calculated this positive charge will create electric field around it, and not all the electric field lines will pass through the circle. Some limited number of electric field lines will pass through our circle, and therefore flux for this circle, which we have done in our classroom, and the flux going through the circle was calculated as q by 2 epsilon 0 times 1 minus that z upon root of z square plus r square. This is the flux which will pass through the circle. We have done it in the classroom. And electric flux from the charge, total flux from this charge. If this is a Q charge, then the total flux around it, total flux coming out of this charge will be according to the Gauss law, and that should be Q by epsilon 0. Total flux which is emitted by the charge is Q by epsilon 0, and out of that total flux, the flux which is going through the circle is this one. And in our question, it is given that the flux going through the circle is 1/3 of total flux, which is Q by epsilon 0. And now you can calculate the value, 22. In this question, we have a charge Q outside the cube, just outside this cube. This charge is just outside the cube. Now, if we recall a particular illustration in our classroom in which there was a sphere of radius a, there was a square surface of radius, a square surface of side length a, and a point charge was placed a by 2 distance above the center of that square surface, then it is a problem from HCV also, and the flux for this square was obtained as Q by 6 epsilon 0 by the logic of symmetry. So, which is independent, this answer is independent of side, and that means if I have another square surface of side 2a and a charge is present above the center of this square, and that distance should be a, only thing is that the charge should be at a half distance. The charge must be at a height which is half of the side. Then you can use this result that flux equals to Q upon 6 epsilon 0. In this case also, the flux of this square will be Q by 6 epsilon 0. And this square which is of side 2a by 2a, you can divide, you can think that this square of the side 2a by 2a is composed by 4 small squares. We can think it like 4 small squares, and all these 4 small squares are symmetrical. So flux for this small square, flux for this particular small square, which is 1/4 of the complete square, by symmetrical logic, flux for this small portion, flux for this 1/4 portion of this big square, 1/4 of this big square will be Q upon 24 epsilon 0, 1/4 of this total value. And if I cut this piece, then it is something like a square of a by a side, and the positioning of charge is at a distance above its corner. So now we can use this result that if a charge Q is at a height equal to the side length of a square, then the flux coming as Q upon 24 epsilon 0. For our cube, such square faces are, I am highlighting those square faces. This square face is example. If you focus on this square face in a separate diagram, just focus on this square face in a separate diagram. This is a square face of side a by a, and that charge which is given in this problem is at a distance from the corner of this square face. So this problem is very similar to what we just discussed. These two are very similar situations. and therefore flux for this square face can be called as q by 24 epsilon 0. And there are three similar faces, like the one is this bottom face. Again, if I concentrate on this bottom face, which is the square of side a by a, then I find this charge q at a distance from the corner of this square. So for this square also flux will be q by 24 epsilon 0. And there is one more similar square, which will be this back square. This back square and the charge q is again a distance from this back square. So flux for this square will also be q by 24 epsilon 0. Whereas total flux for the cube, which is the flux for all six faces, according to Gauss law, this charge is outside the cube. This charge is outside the cube, and cube is a closed body. Whenever a charge is present outside any closed body, the total flux for that closed body should be zero value according to the Gauss law. And out of the six faces, flux for three faces are q by 24, q by 24, and q by 24. So for the remaining three faces, and the remaining three faces are those three faces for which the charge q is just near them. Charge q is just near them. Like this one. This face. The charge q is just near it. And there are similar two faces also. So there are three faces for which the charge q is very close, and for remaining three faces, this charge q is at a distance from their corner. So if I take phi as flux for this surface for which the charge q is very close to its corner, and there are three similar faces, so total flux for those three similar faces will be 3 phi. And for the remaining three faces, it is q by 24, q by 24, and q by 24. That means this 3 phi plus 3 times of q by 24 should be zero value. You get the value of phi. And now solve the question. 23. Electric field is given, and okay. So if I draw it here, there is x and y, and there is some point a 0,1, and potential at that point is 5 volt, and another point B has potential of again 5 volt, and it is at 1,0. And if you read this question, there is a uniform electric field. We all know that in the uniform electric field, equipotential lines, the lines of same potential are straight lines, parallel lines. So if I join these two lines of 5 volt and 5 volt, if I join these two lines which are of 5 volt, this line is basically equipotential line. And then we have another point C, which has a potential of 3 volt. This point C has potential of 3 volt. So make another line. It should be parallel to the previous line, because in the uniform electric field, equipotential lines are also parallel lines. This is also equipotential, but second equipotential is for 3 volt, first equipotential is for 5 volt, and electric field is perpendicular to the equipotential lines. So perpendicular to these equipotential lines, we have electric field. It should be perpendicular to the equipotential lines, and that means electric field makes 45-degree angle with the y-axis or 45-degree angle with the x-axis. And this length, the separation between these two parallel lines, which I leave for you, that d is the distance between these two parallel lines, these two equipotential lines. If the separation is d, which can be obtained, then this electric field E multiplied by d should be equal to the potential difference, and the potential difference between these two lines is 2 volt. So just find out the distance d between the two equipotential lines, which are parallel lines at 45-degree angles. You will get the value of E, and therefore the value for your question, answer for your question. Question number 24. 3 identical particles having this much charge are they are released from rest at the vertices of an equilateral triangle of side length L. How fast is each charge moving when their distance from the center of triangle becomes double? Okay, so there are 3 charges which are present on the vertices of triangle. Let them be Q, Q, and Q, and this side length is L. So this is the initial potential energy, and finally these 3 charges are at double distances, 2L, 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 and all the 3 charges are moving. And because of the symmetry of the problem, we can say that if one charge has a speed of a v, others will also have the same speed, for there is symmetry in this question. So conservation of energy, initial potential energy should be final potential energy of electrostatic and the final kinetic energy. And initial potential energy for these 2 charges Q and Q can be K times Q1 Q2 over L, and there are 3 similar pairs. 3 similar pairs of charges are present, so the total potential energy will be 3. In final potential energy, again you have to put the new separation 2L, and plus kinetic energy of one particle will be half mv square, and there are 3 similar particles, so it should be 3 times. Now calculate this. Calculate and get your answer. 25. Insulating rod having linear charge density lambda and the linear mass density itna is released from rest in the uniform electric. Okay, there is a uniform electric field. So this uniform electric field is at an angle of 60 degree. Inside that we have some rod. Okay, there is a rod like this. According to our question, there is a rod which is positively charged. So it has some positive charge. Length, lambda, mass, everything is given. Mass is all given. Remember, this is released from rest. And whenever a charge is released at rest, if a charge is released at rest and electric field is uniform, that charge will move along that. And this wire will start moving parallel to electric field. This wire will move like this, parallel to electric field. Any stationary particle in the uniform electric field will always move along the electric field. Means at some, after certain time, this wire will be like this, having instantaneous velocity parallel to the electric field. It will move along the electric field because it has no initial velocity. And according to Newton law, a particle without initial velocity will move in the direction of the force applied to it, and the force will be along the direction of electric field. Therefore, so it is basically 1D motion, a straight line motion. The rod will move like a straight line path. It is 1D motion, and therefore the velocity can be obtained by third equation, which is v square equals to u square plus twice of as. Here this u square is 0 because it starts from rest. For acceleration, take force QE over this mass, and then displacement is given. Just calculate, you'll get your answer. Thank you very much.